teknologi secara kreatif, inovatif, dengan dinamika. Paradigma pendidikan kami adalah memberi peluang bagi yang ingin berusaha untuk maju dan meraih kemandirian dengan penguasaan ilmu dan teknologi secara kreatif, inovatif, dengan dinamika. Paradigma pendidikan kami adalah memberi peluang bagi yang ingin berusaha untuk maju dan meraih kemandirian dengan penguasaan ilmu dan teknologi secara kreatif, inovatif, dengan dinamika. Paradigma pendidikan kami adalah memberi peluang bagi yang ingin berusaha untuk maju dan meraih kemandirian dengan penguasaan ilmu dan teknologi secara kami menjadi sebuah universitas yang unggul dalam pengembangan ilmu dan teknologi dengan berlandaskan nilai-nilai Islam untuk kemaslahatan umat. Kami menjadi sebuah universitas yang unggul dalam pengembangan ilmu dan teknologi dengan berlandaskan nilai-nilai Islam untuk kemaslahatan umat. Paradigma pendidikan kami adalah memberi peluang bagi yang ingin berusaha untuk maju dan meraih kemandirian dengan penguasaan ilmu dan teknologi secara kreatif, inovatif, dinamis, dan beradaptasi. Visi kami menjadi sebuah universitas yang unggul dalam pengembangan ilmu dan teknologi dengan berlandaskan nilai-nilai Islam untuk kemaslahatan umat. Paradigma pendidikan kami adalah memberi peluang bagi yang ingin berusaha untuk maju dan meraih kemandirian dengan penguasaan ilmu dan teknologi secara kreatif, inovatif, dinamis, dan beradaptasi. Visi kami menjadi sebuah universitas yang unggul dalam pengembangan ilmu dan teknologi dengan berlandaskan nilai-nilai Islam untuk kemaslahatan. Paradigma
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, this is Inta Asuti speaking, a moderator for today's conference. Thank you very much for joining us. The time is now pointing 7:57 a.m. in Jakarta time, in which we have to immediately start the International Virtual Conference of CIMAPS 2020. We are waiting for more participants at the moment. Many more still on the go to join us on the Zoom and YouTube channel of Teknik Sipil Universitas Muhammadiyah Yogyakarta. We will start soon in 3 minutes. Thank you for waiting. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, ladies and gentlemen. Let me introduce myself. I'm Pinta Astuti from Department of Civil Engineering, Universitas Muhammadiyah Yogyakarta, will guiding all of you as moderator for today's event. I'm speaking from Yogyakarta, Indonesia. First of all, I would like to thank to Honorable Dean, Faculty of Engineering, Universitas Muhammadiyah Yogyakarta, Associate Professor Jazaud Iksan, PhD, and the Head of Department of Civil Engineering, Puji Harsanto, PhD, for supporting this event. Also, thanks to Dr. Ani Hairani, a chairperson of today's conference, for organizing this conference. Thank you very much for coming, Bapak Gatot Sukmara from Balai Teknik Jembatan, Direktorat Bina Teknik Jalan dan Jembatan, Ministry of Public Works Republik Indonesia. Also, Ibu Dr. Rahmita Sari Rafdinal from Maintenance Engineering Group, Research and Development Division, PS Mitsubishi Construction Co. Ltd., Japan. I also would like to welcome to all keynote speakers and participants to the International Virtual Conference of Civil Engineering and Material Science Application Symposium, CIMAPS 2020, within Cutting-Edge Innovation in Civil Engineering and Material Engineering Science. This symposium is a focal conference and part of International Conference of Sustainable Innovation ICOSI 2020, organized by Universitas Muhammadiyah Yogyakarta on 13 to 14 October 2020. It's my pleasure to have this event in which we have 4 distinguished keynote speakers to share their precious knowledge and research experiences in the field of civil and material engineering sciences. They are Professor Yong Kim from Texas A&M University, United States of America. Good night, Professor Kim in America, 12 hours behind from Indonesian time, now still Tuesday night in America. Thank you very much for joining us today. And then Professor Hidenori Hamada from Kyushu University, Japan. Good morning, ohayo gozaimasu, Hamada Sensei in Fukuoka, Japan.
Good morning.
Thank you very much for joining us. And then Professor Wei-Sing Huang from National Central University, Taiwan. Good morning, Professor Huang in Taiwan. And Professor Agus Setio Muntohar from Universitas Muhammadiyah, Yogyakarta. Good morning, Professor Agus. Thank you very much. On behalf of the CIMAPS 2020 organizing committees, I would like to thank you for accepting our request to be a keynote speakers in today's conference. We really appreciate your contributions. So to begin our event, we will have an opening speech from the Dean, Faculty of Engineering, Universitas Muhammadiyah, Yogyakarta. Let's welcome Bapak Associate Professor Jazaul Ihsan, PhD, to deliver an opening speech. So for Bapak Jazaul Ihsan, the stage is yours.
Assalamualaikum warahmatullahi wabarakatuh. The Honorable our keynote speaker, first Prof. Kim. Good night from Texas University, United States. Second, Prof. Huang from National Central University, Taiwan. Good morning, Prof. Huang. And also Prof. Hamada from Kyushu University, Japan. Good morning, Hamada Sensei, ohayo gozaimasu. And also Prof. Agus Muntohar from Tas Muhammadiyah, Yogyakarta. Selamat pagi, Pak Agus. Good morning. And Dr. Puji Harsanto as a head of Department of Civil Engineering, Faculty of Engineering, Tas Muhammadiyah, Yogyakarta. And dear colleagues, friends, and all participants, good morning, ohayo gozaimasu, selamat pagi. Behalf of Faculty of Engineering, I would like to express our warm welcome to all participants to Civil and Material Engineering Symposium or CIMAPS 2020. I think now it is hard to live in this situation. This pandemic affects us to do many things, but I do believe that this situation do not bring down our spirit to join and to share our knowledge with overall country in this conference. It has take time that such event took place to sharing idea, concept between various aspects of civil engineering and material science in order to understand in more deep of how this aspect intertwine in our life. And in this year, the conference took theme cutting-edge innovation in civil engineering and material science, and we should expect critically challenge ahead in fully realizing and the spirit of the term. We would proactive manage to manage change we face each and every day. Let us all our care, competence, and energy for influence how aspect with strong idea related to the theme. In this event, held under the conjunction with International Conference on Sustainable Innovation, ICOSI, Universitas Muhammadiyah, Yogyakarta. In the CIMAPS event, CIMAP, the committee received several papers from Japan, Taiwan, Malaysia, of course, from Indonesia. I'm grateful to many experts who come to share their knowledge in this day. I also welcome to many representatives for the country and also from university who have joined this conference. Dear college and all participants, member of organizing committee have been working hard, very hard, I think. I would like to thank from their dedication, time, and effort. I also thank to our partner, individual, and organization, and also volunteer. Without their effort, we would not, we don't be able to create the good conference as today. So I wish you every success with this conference, and I'm looking forward to learn about the outcome. I think enough for my speech. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Bapak Jazaul Ihsan, for very warm welcome and opening speech for today's conference. Distinguished guests, ladies and gentlemen, before we enter to the main menu for this conference, I will inform you that today we have 4 sessions of keynote speakers. Each session consists of 20 minutes presentation and followed by 10 minutes of discussion. I will remind to keynote speakers when 5 minutes left. So if you have question or comment for the keynote speakers, please drop your question in the room chat, including your name, affiliation, and your questions. Then I will pick up some questions to be answered by keynote speakers, depend on the available time. Now let me introduce our first honorable speaker for today's session, Professor Yong Kim. So Dr. Yong Kim is a professor in the Zachary Department
the keynote
of
speakers,
Civil
please
and
drop your question in the room chat, including your name, affiliation, and your questions. Then I will pick up some questions to be answered by keynote speakers, depend on the available time.
The Texas A&M
Now
University
let me introduce our first honorable speaker for today's session,
Dr. Kim's
Professor Yong Kim.
has focused
So
on
Dr. Yong Kim is a professor in the Zachary Department
the keynote
of
speakers,
Civil. Please drop your question in the room chat, including your name, affiliation, and your questions. Then I will pick up some questions to be answered by keynote speakers, depend on the available time.
The Texas A&M
Now let me introduce our first honorable speaker for today's session,
Dr. Kim's
Professor Yong Kim.
has focused
So Dr. Yong Kim is a professor in the Zachary Department of Civil. Please drop your question in the room chat, including your name, affiliation, and your questions. Then I will pick up some.
Drop your question in the room chat. After the video presentation, Professor Kim will answer your question because now Professor Kim also joined us in this meeting. So for technical committees, please proceed Professor Kim video presentation. So ladies and gentlemen, please welcome Professor Yong Kim.
So this is Yong. So are we supposed to play the video I sent you?
Okay, Professor.
Okay, good. So are you playing over there?
Yes.
Okay.
Okay, Professor.
Okay, good. Selamat pagi. Good morning, everyone. Over there? It's great to see you all. Okay. And thanks for invitation to this excellent event. I'm personally great honor to be with you this morning, and it is my great pleasure to share some of my research with Indonesian engineering community. This is my first time to be with you. Selamat pagi. This is excellent opportunity. Good morning, everyone. Over there? So today, it's great to see you all. Okay. What I like to do, thanks for invitation to this some of my research excellent event. Regarding I'm personally great honor to be with you this morning, and multidisciplinary. It is my great pleasure to share some of my research with Indonesian engineering community. This is my first time to be with you. Selamat pagi. This is excellent opportunity. Good morning, everyone. Over there? So today, it's great to see you all. And thanks for invitation to this some of my excellent event. Regarding I'm personally great honor to be with you this morning, and multidisciplinary. It is my great pleasure to share some of my research with Indonesian engineering community. This is my first time to be with you. Selamat pagi. This is excellent opportunity. Good morning, everyone. Over there? So today, it's great to see you all. And thanks for invitation to this some of my excellent event. Regarding I'm personally great honor. So
I'm sorry for the
yeah, I can
trouble.
hear a lot of echoes. I don't know what's going on. Is it just my problem or anybody here?
No,
Same.
I think it's double sound. Sorry for the problem. Let's start from the beginning of this video, Professor Kim presentation.
Because they can improve transportation and energy, water and waste systems, and also create more sustainable urban environment. So we are doing excellent, very important job. Selamat pagi. Good morning, everyone. It's great to see you all.
Sorry for the problem.
And thanks for
Let's start
invitation
from
to this
the beginning of this
excellent
video,
event.
Professor
I'm
Kim
personally
presentation.
great because they can improve transportation and energy, water and waste systems, and also create more sustainable urban environment. So we are doing excellent, very important. This is my first time to be with you. Selamat pagi. Good morning, everyone. It's great to see you all.
Sorry for the problem.
And thanks for
Let's start
invitation
from
to this
the beginning of
excellent
this video,
event.
Professor
I'm
Kim
personally
presentation.
great because they can improve transportation and energy, water and waste systems, and also create more sustainable urban environment. So we are doing excellent, very important. This is my first time to be with you. Selamat pagi. Good morning, everyone. It's great to see you all. And thanks for invitation to this excellent event. I'm personally great because they can improve transportation and energy, water and waste systems, and also create more sustainable urban. Okay, I think the problem's still there. So how about I present on live? Would that be better? I think we better not to play the video. Can you hear me, by the way? Can you hear me?
Yes.
Okay.
Thank you very much.
So how about I
Sorry
present?
for this trouble.
That's okay. You know, for these days, this problem happen all the time. So can I share my screen?
Yes, please, Professor Kim.
Okay, let me. Wait a minute. Can you see my screen?
Yes, very good.
How about now?
Yes, please. Okay, very good.
Okay, then why don't we do this way?
Oh, sorry, Professor.
No problem. Again, selamat pagi.
Selamat pagi. Thank you very much.
All right, so great to see you all, and it is my great honor to be with you tonight. Today, in the morning over there. And my name is Yong Kim, and I'm a professor in Texas A&M University. So today, what I like to talk about is my research, multi-scale, multidisciplinary research to advance materials and infrastructure systems. So we know that U.S. infrastructures are not in good shape. We have a lot of issues. Average grade of infrastructures from ASCE is D+. So it's pretty bad. Roads are even worse, D, and the bridges are C+. So we have to spend a lot of money for the next decades. So it's a really important business. Everybody should be doing a good job. And that's actually good sign for us because we have a lot of work to do. National Academy of Engineering in the United States, they designated total 14 grand challenges in the 21st century. And one of them is about infrastructure. They said we need to restore and improve urban infrastructures by doing better design and advancing materials, because we can improve transportation, energy, water, and waste system, and also create more sustainable urban environments. So as we know, infrastructure is one of the very important problems, and we should doing a great job on that. But it's not easy. We have a lot of threats, and mostly from climate change. We see disasters from everywhere, pretty much every day. In United States, we got a lot of rains, flooding in Midwest, and sometimes very cold winter, and hurricanes, fire on California. So a lot of issues because of climate change, and that issues is actually from about 0.5 degree temperature up for the last several centuries. So that small increase of temperature really create a lot of issues. And scientists predict it can be even about 6 degrees up next 100 years if we don't do a good job. And they said also about 1.5 degrees C, total ecosystem will be failed. So we really need to do a better job, and we need to reduce CO2, and we need to think about the environment, not just development for the growth. So there must be a lot of things we can do, but in my lab, my research, I am focusing on the materials for better infrastructure systems. So we are interested in advancing civil engineering materials and sustainable infrastructures. And we love mechanics. So we do a lot of mechanistic research for analysis and design of materials and structures. Particularly, we do a multi-scale, multi-physics characterization and modeling of engineering materials. For some complex materials like viscoelasticity, damage, cracking, and durability with environmental conditions as well. So we do testing and modeling. We combine together from very small scale, nanometer scale to meter, kilometer scale, structures. So our research methods are, simply speaking, multi-scale, multidisciplinary. As you can see these slides, this is kind of snapshot, kind of summary of my research. we combine different aspects. We work with chemistry, physics, mechanics, material science, and even data science. So once again, we looked at problem from very small molecular level, atomic level scale for fundamental understanding, and micrometer, millimeter, centimeter, pretty much laboratory testing scale, and the meter, kilometer scale for structures. And we combine all together, and we link information between scales, try to understand and the resolve the issue we are talking about today. So one of example I like to spend a little bit time this morning is roadway problem. Roadway is one of my primary areas, and here is a snapshot of the research. Again, we looked at the problem from very small scale, and then upscale and linking scales. From testing and modeling, you can see there some molecular level study, atomic microscopy, rheometer testing, mixture testing, simulation of it, and even roadway structural level. So we do this research, and sponsored by U.S. government, National Science Foundation, and the U.S. Department of Transportation. So I like to share a little bit of my research outcomes this morning with you. So here, just quick summary. We don't have enough time. I know I have only 20 minutes, so it's really impossible to talk any details. But what I can show here is we can do simulation of molecular level phenomena such as aging of bitumen in the roadway. So we try to understand what the fundamental mechanism of aging related with oxidation and some change of chemical group. And on the right hand side, a little bit of upscaling, micrometer scale, atomic force microscopy. We can measure the surface topology of the bitumen aged, and then we can also model the system. I mean the material for the prediction of properties. As you can see, some result in the slide. So this very small scale, molecular level and micro level information can be used for larger scale simulation and modeling. And such as here, I like to show that like a 150 millimeter diameter typical specimen you can make in the laboratory. You can do compaction, and then we can do 3D X-ray CT to characterize the microstructural details. Then, as I mentioned, we do a lot of mechanics, particularly computational mechanics, micromechanics. In here, like finite element simulation for the microstructure by having small scale testing, such as nano indentation testing of particles, and rheometer testing for viscoelastic properties of surrounding matrix, and also fracture properties of surrounding matrix, so that we can get the information of individual components, and that individual component can be used for like a virtual testing, like a simulation of testing. So here, as an example, you can see like a semicircle, like half circle there. And in our community, people do this testing quite often. You can compact specimen and cut it in half and take a notch at the bottom, and then a simple 3-point bending testing can be done for simulation of the crack propagation at the tip of notch to the top, and they can evaluate mixtures. Okay, but then we can do actually model this. As you can see here, we can generate microstructural details, and that can be simulated here I play the testing virtually. So this video may be large file, so it works not very smooth, but I think you can see that crack develop at the bottom of at the top tip of the notch and then propagate to the top. So what I can say is we can simulate this testing in the computer using the computer, not in the laboratory. So we can save a lot of time, and then the model validation will be conducted. So here basically the model can be compared with experimental data. So from the prediction, we will be able to characterize important material properties that we can use for design of structure like a roadway. So roadway modeling can be done, macro scale roadway modeling. Here again, just simple snapshot, the mixture level understanding, mixture level testing, mixture level modeling. From there, fracture properties can be inputs of like a roadway modeling to predict cracking and any kinds of other damage associated with environmental condition like water and temperature. So we do this job using fracture mechanics, cohesive zone fracture mechanics for prediction of cracking, and has been validated with some experimental data and field performance. So I'm talking about different lengths of scale and their interaction to better design and the better selection of materials and even better prediction of the life and performance. So this technique can be used like this. As you can see here, the roadway model. The structure is layer structure. You have different layers. Top, typically like asphalt or concrete, and then base layer, and soil sub-base and subgrade. And just an example to show how your roads are under damage, like a crack developed because of this repeated truck loads. So we can simulate this and predict the performance and even life prediction, which is not easy, but we are trying to do that. So how we can use this approach for even real life practical engineering? Well, we can do that, simply evaluation of the effect of design variables. Like what if you change your materials? What if you change your particle gradation? What if you change your glue, binding material? What if you change structural configuration? So there are a lot of things that you can do for the optimum design of mixtures and optimum design of structure together. So that's what I'm talking about. We can actually do optimizing your design of both mixture level and structural level from better selection of component material, and the model, the mechanistic model can do the job very nicely. So here is just some examples, like what if you change your damage evolution because of different type of base material, like granular base or concrete base with different layer thicknesses. What happens if you change your mixture gradation, like particle gradation and volume fraction of it? What if you change your material property of your mixtures and layer thickness of your surface? So then this kind of parametric analysis can give you nice information for the optimal design of it. So far was kind of quick overview of one research avenue, which is roadway research. But similar technology, multi-scale, multidisciplinary, can be applied to other problems. And I just want to mention a few other potential problems we are actually working on. So here is a problem regarding soil stabilization. We are working on this project sponsored by US DOD, Department of Defense, US Army Corps of Engineers. So they're interested in developing stronger foundation, soil foundation for military structures. Military, they're not typical, right? They're very heavy, large, and not similar to ordinary life we are facing. So they try to develop new type of stabilization for soil and aggregate system using different special additives. So we are looking into several different kinds of additives, organic and inorganic, which should be much better than conventional additives. So we use multi-scale research concept in this project, looking at from molecular level to scanning electron microscopy and even mixture level and structure level altogether. So that's one project I can say we do a great job with the multi-scale, multidisciplinary aspect. And here is another quick overview of research to better understand the interface transition zone in cementitious mixtures. In like a concrete, you have aggregates and cementitious binder, and there is an interface which is typically a weak zone. And when we use like a secondary materials like a recycled aggregates or industrial byproducts like a fly ash or slags for binding material, then your interface will be different from conventional ordinary Portland cement concrete. And we are interested in what happened and what will be controlling factor to make the different interfaces, right? So that is a major purpose of this project, sponsored by National Science Foundation. So we looked at the interface and 4 different aspects and combine all together like a mapping among those to better understand what happens. So we do small scale microscopic characterization, chemical analysis using energy dispersive X-ray spectroscopy, and nanomechanical characterization using nano indentation, and typical laboratory level 3-point bending beam testing. So we combine all together and try to understand the formation of interface and controlling factors in terms of the quality of interface. So we finished this project about 2 years ago. We got many publications out of it. And another one I like to just quickly visit is the project one of my graduate students is working on right now, Dian Setiawan. I'm sure he is from Yale University. So I guess this invitation is also related with his join with me at Texas A&M University. So Dian is working on kind of development of like asphaltic rail track systems that can be very useful in Indonesia. Hopefully this is more sustainable and better performing than conventional rail tracks, some problematic rail tracks in your country. So Dian's interest is to develop a new asphaltic rail track system, and for computational modeling and simulation of the structure from the material properties we can think of for the optimal structural system development. So he just started this project, so we will be expecting excellent results in a few years later, and that's my hope. And this is basically some kind of snapshot from somebody else, like a Korean research team started this project several years ago. So I just put those figures just to show what the project is about. Okay, so anyway, this also can be benefited by our multi-scale, multidisciplinary, multi-physical research aspects. So my concluding message is very simple. I think this is basically the theme of this symposium. We should be using material science. We should be based on science for better engineering. In fact, Leonardo da Vinci, long time ago, the genius, he said this: those who are obsessed with practice but have no science are like a pilot out with no tiller or compass. So he knew that without science, engineering is limited. So to enlarge horizon of our engineering, we need to really have science in there. And I'm talking about basically multi-scale, multidisciplinary aspects. So just acknowledgements before I finish. I have been very fortunate having a lot of sponsorship from government supports, industry and state agencies and international sponsors like Korea, Brazil, and so I was very fortunate, and I really appreciate their support. And above all, the biggest contributor of my research is my graduate students. Okay, so without students, it's really hard to make anything changes. If I may have about just 1 more minute, I'd like to just quickly introduce our new center, the Center for Infrastructure Renewal. So CIR is a national leader, national hub, international hub to develop really transformative solutions for infrastructure, particularly aging infrastructure, to get better renewal and development. So we try to have very innovative approaches to make a longer lasting infrastructure with less time and lower cost. So it's a really excellent facility, about 140,000 square feet, more than 10 labs with 9 departments come together. So here are the number of labs. You can imagine anything, they are there. So, materials lab, asphalt, concrete, assessment, corrosion, protection for military purpose, power grids, soils, unbound materials, and even transportation. So it's a very, very nice equipment, facility, laboratory building we like to promote. So if you have a chance to visit our campus, please let me know, and I can get you a tour the laboratory facility. With that, I conclude my presentation, and here is my email. So please reach me if you have any discussion and questions or things to talk with me. And I will conclude my presentation with terima kasih. Terima kasih. All right, thank you. Thank you for your attention.
Thank you very much, Professor Kim, for a very nice presentation. So I would like to invite some question from the chat, and I will deliver the presentation. So the first question from Professor Agus, I will read the question. How do you deal with the ME pavement design, and how to characterization the stabilized subgrade for ME design? So maybe Professor Kim, please.
Yeah, ME design is great product. U.S. government spend a lot of money for next generation pavement design, which is ME, mechanistic and empirical. And but I'm not a. I don't use ME a lot. I do develop a more mechanistic design approach, like I showed you today. But if I may talk about ME design regarding stabilization, I would say, well, when you get the stabilization of soil, you will get different property, probably higher stiffness, and that could be input for the design process. I think I can answer that question in that way. But one limitation of ME is it cannot really address damage properly. That is my personal opinion, but you don't have a very rigorous damage model, damage prediction feature in ME because of practicality. You cannot actually do it to finish a design for 20-year, 30-year design within about 20-minute simulation. So the model or the way should be very simple, and ME cannot take care of that. But it's a very nice product. But anyway, for the question about it, I think it's basically elastic property because of stabilization, afterwards.
Okay, thank you very much for your answer. Maybe for Professor Agus, is there any other question about your previous question? And for next question from Dr. Ahmad Zaki. It's very interesting research area, and Dr. Ahmad Zaki wants to know about how we can input the climate change parameters in the finite element model simulation and the experiment. Maybe you
Yeah,
have
it's a very good question. And Dr. Zaki, you are asking very tough question. I don't know how to do, to be honest with you, but I can say that it has to be multi-physical. If you think about climate change, it's really, I mean, you know, nobody can predict the weather accurately. So then, you know, if you have a very good accurate prediction of weather, we can possibly use that data into our model for variation of temperature and variation of moisture. And that is not easy. I mean, it's not a joke. It has to be a lot of data. So I think rigorous inclusion of this weather or climate input into the finite element simulation is not easy. I haven't done that yet. I don't know how to do, but I think it should be based on some multi-physical component coming in, like your moisture transfer, diffusion, and the heat transfer, and then associated with you know, cracking and the deformation with that. And that should be mechanically modeled in the problem. Then you might be able to do some better job prediction of those. But again, it's not easy to me. It's really tough to do. But I think that's the right direction. We need to go for that direction. But to be honest with you, I haven't done that yet before. But one of my projects sponsored by Department of Energy is actually multi-physical crack modeling. So we try to you know, predict the desiccation cracking for the engineering barrier material. I think one of keynotes today is about that, you know, nuclear waste repository. So we try to develop a model for like a soil, you know, when you have drying and the moisture coming in and out, then how your crack actually changes. So that's something I'm working on. So, you know, maybe this is kind of similar, but it's very tough problem, I believe. So
okay.
my answer is not great, I know, and sorry for that, but
okay,
yeah,
thank you, thank you very much for your answer. And one more last question from audience, from Mr. Shaiful from UMY. Indonesia has a lot of pit area, and we face many problems in providing existing materials to improve the quality of roadway pavement. Can it be applied in this condition, or do you have any suggestion about this question, Prof. Kim?
So I think the question is asking about like a improvement of soils, maybe, or
soil
pit area. So
pit area.
Yeah, so I think it's about improvement. Typical way is adding some. You know, it can be physical adding or chemical adding. You can expect some chemical reaction for some between materials, and or sometimes just physically reinforcing by putting some are rigid additives or different kinds of things. So I guess there is a way. Again, I don't know exactly. I'm answering to the question, but I think the problem can be improved by doing some more engineering, basically either physical addition or chemical addition, and then property gain will be checked with your specification to be met for any kinds of construction. So I think there is a way to do.
Oh, okay. Thank you so much for your answer about this matter. And I think still still so many questions.
Oh yeah, I can see many questions.
Yeah, but I think there is no more time.
No more time.
And we have to move on to the next keynote speaker. Thank you very much for your presentation. And we are very sorry for today's technical problem.
Oh, no problem. So,
thank you so much.
Sorry for not answering other questions because of limitation of time, but I think this question is recorded, so maybe
yes,
you can share with me later, or the person who asked question just directly contact me. You know, I have an email, so you can just talk with me afterward. We can discuss.
Okay. Yes, thank you very much, Professor Kim, and we will summarize some question and we will email you later.
Sure.
Thank you very much. Thank you
All
very
right.
much. We
Thank
really
you so
appreciate
much.
your contribution.
Okay.
Thank you very
Okay.
much. Okay. Distinguished guests, ladies and gentlemen, let's move on to the second keynote speakers. Let me invite Professor Hidenori Hamada to give a lecture. Yeah, before starting, I will show a brief CV of Professor Hamada. Actually, Hamada Sensei is my doctor supervisor in Kyushu University, Japan, that I left 16 days ago. He is a professor in the Department of Civil and Structural Engineering, Kyushu University, Japan, since 2009. His previous research career was at Port and Harbor Research Institute and Port and Airport Research Institute for 20 years. His research interests are environmental friendly concrete material, life cycle management, electrochemical research on corrosion and corrosion protection. So today, Hamada Sensei will deliver a lecture entitled Seawater Utilization in Concrete Production for Future Water Stress World. So Hamada Sensei, are you ready to proceed your presentation?
Thank you. Thank you, Pinta-san. Dr. Astucci.
Thank you so much, Sensei.
So shall we share my PowerPoint files?
Yes, please, Sensei.
Oh, sorry. Oh, just a moment, please. Thank you. Thank you, Pinta-san. The title of my presentation is Seawater Utilization in Concrete Production in Future Water Stress World, especially from the viewpoint of corrosion prevention of steel in concrete. So today's topic is a research topic carried out in Kyushu University and also some other universities in Japan recently for 5 or decades. So firstly, I'd like to express my sincere thanks to the organization for inviting me as one of Keynote's invited speakers. It is my great honor to be here. Thank you very much again. So I'd like to start my presentation with first topic, why now we need to use seawater for concrete production. I suppose many of you wonder it, why we have to use seawater for concrete. So actually, our world is now facing water scarcity. First step and next step is water stress, and finally, we meet water crisis. However, it is very difficult to realize it in the city in most countries. Actually, I cannot feel it. I'm living in city areas in developed countries. So what is water scarcity? So water scarcity is a lack of freshwater resources to meet water demand. A mere 0.014% of all water on Earth is both in fresh and easily accessible. So of the remaining, 97% is saline and a little less than 3% is hard to access. Sorry. All right. So then what is water stress? So more than one in every 6 people in the world is water stressed. meaning that they do not have sufficient access to potable water. Then, what is a water crisis? The water crisis is not enough potable water for a given population. The threat of water crisis is realized. So it is just estimation, but in 2025, 2 by 3rd of world population will be suffered from water shortage, even drinking water. It is just estimation, but actually water crisis is quite very close to our society. So this map is showing the condition of Earth's water condition in 2040. This is by World Resources Institute. So we can see from this map, the crisis is very, how can I say, realized to us, especially in the red-colored countries. So including Indonesia, I think. So this is a description in the some newspapers. It said water is the new oil in 21st century. So Goldman Sachs estimate that global water consumption is doubling every 20 years, and United Nations expect that demand for pure water will outstrip the supply by more than 30% by 2040s. It is from Times I see almost 5 years ago. So in Australia, brokers in urban areas are buying up water rights from farmers. So in US, rural residents around the US are trying to sell their land and water to multinational water bottlers. So this is a fact which is described in the Times about 5 years ago. I saw it. So this is a background. We are now doing research on seawater utilization in concrete production. Then, how is the present situation of seawater usage in concrete production? This is a second topic of this presentation, my presentation. So first, activities, formal activities in Japan is by JCI, Japan Concrete Institute. So JCI established a technical committee on the use of seawater in concrete. Activity is continuous. It was continuous from 2012 to 2015. So the background is just I explained. In the field of concrete, billions tons of fresh water is consumed annually every year for mixing, curing, and washing machineries. Seawater is presently not permitted to be used for these purposes. So, active use of seawater in the field would help more effective use of freshwater resources. So, at that time, the committee chairman was Professor Nobuaki Otsuki, belonging to the Tokyo Institute of Technology. Now he is a professor emeritus of same university, Tokyo Institute of Technologies. So there are actually two aspects, positive aspect and negative aspect for seawater utilization in concrete production. In positive aspect, some researchers reported it is not so bad to use seawater with mineral admixtures. Negative aspect is, as all of you know, all the standards in the world inhibit using seawater as mixing water for reinforced concrete. And also, almost all the authorities in the world are against to use seawater for concrete mixing. As think almost all think so. So this diagram showing the result of literature survey carried out by Dr. Nishida, now belonging to PARI, formerly belonging to the Tokyo Tech. He checked totally 68 papers on seawater utilization for concrete production from all over the world. So as you see, if the concrete is mixed with only OPC, ordinary Portland cement, the positive result is only 23% in blue-colored position, and negative result is 37%. But if concrete is mixed with blast furnace slag or fly ash with mineral admixtures, then the result for positive is over 50%. In case of blast furnace slag, 63%, and fly ash, 58%. So from this survey, we could recognize that the usage of mineral admixture is inevitable for producing the concrete by mixing with seawater. So this is the first step we could get for concrete production by seawater. So then, what is problem of seawater use for concrete production? Physical properties, long-term durability, or chemical properties. So we checked our previous experience on seawater utilization, and seawater harmful for cement hydration. We checked it. The result is it is not harmful, almost no problem. And is seawater harmful on fresh concrete properties? Slightly, very slightly, but it is not. It can be said not harmful. It's the same situation for tap water mixing and also seawater mixing. So, is seawater harmful for initial strength development or long-term strength development? It is not harmful, no problem. So, this diagram is shown in the doctoral thesis by Dr. Adivijaya in his doctoral thesis of Kyushu universities. This one showing the strength change from 28 days under 27 years old with seawater mixed concrete. So you can see from this diagram, 27 years old concrete shows the 1.5 to 2.5 times strength level than initial strength at 28 days. So concrete strength is not affected by mixing the seawater concrete for long term. So 27 years after, it is no problem. So then, what's the problem for seawater mixing? Is seawater harmful for durability? For carbonation, maybe no. This is shown by the research by Adivijaya, Dr. Adivijaya. And chloride attack, sure, yes. This is the most serious problem. So alkali-silica reaction, maybe yes, but by mixing mineral admixtures, it can be prohibited. For chemical attack, maybe no. So the most important and serious problem is the steel corrosion. How to prevent the steel corrosion inside concrete with seawater. Then next question is, can we use seawater for concrete production safely? What countermeasure is necessary for corrosion prevention of steel in seawater mixed concrete? So this one is this one showing the deterioration process of chloride attack of concrete divided to stage initiation and propagation. So the boundary is sometimes it's an initiation of corrosion and sometimes it's a occurrence of cracking. Anyway, the chloride content inside concrete is a key factors affecting the initiation of corrosion of steel bars inside concrete. So normally, if we use tap water, pure water for concrete mixing, the chloride content level is 0 to 0.6 kilogram per cubic meters. However, if we use seawater for concrete mixing, the initial chloride content level is around 3.0 kilogram per cubic meters. And if we also use unwashed sea sand for fine aggregate, then the initial chloride content level is around 4.8 kilogram per cubic meters for standard mix proportion. So the problem is initial chloride content is quite high by mixing seawater or by using unwashed sea sand. So, however, there is a very interesting and important research result by Dr. Daria Pata, Kyushu University 2019. This diagram showing the chloride threshold for corrosion initiation in the concrete mixed with several different kinds of mineral admixtures. So, if fly ash is used, then the maximum threshold level is 6.64. Water to binder ratio is 0.4. And also, if we use blast furnace slag, the maximum chloride threshold level is 6.0. For water to binder ratio is 0.4. This is much over the seawater chloride content of concrete, seawater mixed concrete, around 3.5 kilogram per cubic meters. So this results showing the chloride content, threshold content level can be increased by mixing adequately the mineral admixtures. So I think this research result is also a result for Dr. Nishida's literature survey showing the effectiveness of mineral admixtures. So I would like to introduce several experiences of CO2 mix existing concrete structures in Japan. This one is a lighthouse located in the coastline in the Nagasaki Prefecture in Kyushu Island. This one is constructed more than 50 years ago by using seawater for mixing waters. But present condition is a right side photograph. As you see, the condition is very good. No deterioration on the concrete surface and also no sign of corrosion inside steel bars. So this is a good example of CO2 mixed concrete structures. As you see, a very good condition. So I would like to introduce one trial done in Kyushu Universities by master student and doctor student. Application of corrosion prevention, a calcium nitrate-based corrosion inhibitor. So this is a specimen condition. Just you see a left side, bottom left side photographs. She tried to cover the steel bars by cement paste, including a corrosion inhibitor, firstly, and cast the CO2 mixed concrete. Then the steel bar could be kept in a stable condition for a long time. This experiment is now going on. So I think we can present it in near future, the test result. Anyway, this is a very simple trial, but I think it's a very good idea to do. So this one is a photograph. These photographs are taken by me in Vietnam. The Vietnam engineer explained to me these structures are made by mixing concrete. By mixing concrete with seawater. So by looking at this one, he asked me how we can use seawater for concrete production. At that time, I answered immediately, it is very difficult to use it. But now I think I should answer it can be, but with adequate countermeasures to prevent steel corrosion, we can use seawater for concrete production. So I'd like to conclude my presentation. In near future, seawater mixing will be inevitable technique in concrete engineering almost all over the world. So it is necessary the collaboration of concrete engineer and also corrosion engineer in the civil engineering field. This is very important. So I visited Yogyakarta 15 years ago. I couldn't visit this time, but I hope someday I could visit again. Very impressive. So this photograph is also I took in Yogyakarta to meet the person in Yogyakarta. Very impressive. And myself, 15 years ago, still 44 years old, I visited Yogyakarta. So thank you very much for your kind attention. This photograph is a graduation ceremony of Dr. Astusi in Kyushu University in last month. So thank you very much for kind attention. Thank you. Thank you very much for attention. Thank you again.
Ani, I think you are muted.
Muted.
No, Ani should be moderating this because I cannot hear anybody.
Yes. Can you hear?
I can hear you, Doctor, but I cannot hear from Ani Hairani.
Peter-san, can you hear my voice? Is it
Yes.
okay?
Yeah, I can hear you very well.
Thank you. Shall I answer to the question?
I think there is a question from Rezeki. So maybe, Professor, you can answer to the question. Meanwhile.
Okay. Thank you very much. Thank you. So every ocean have a different salt level. I see. So, but normally the standard level is the 3.3 for chloride sodium. It's slightly moving, but the standard level is same. So before using CO2 for concrete, I think it's better to check the chloride level inside concrete before mixing. Is it okay? So next question, do we need use a special treatment to use CO2 to make concrete? According to Nishita-san's report, that by using PFC and CO2 resulted in more positive. Yes, so we don't have a now standard mixed proportion for concrete mixed with CO2, but now we are thinking that using blast furnace slag, fly ash, or some other kind of mineral admixture is inevitable to mix concrete by using CO2s. So firstly, we should check the steel condition by mixing actual concrete, expected concrete. And if still it is not enough, then we have to think the application of cathodic protection or surface coating or some more techniques to prevent the steel corrosion if we use seawater for concrete mixing. However, first choice is to mix the mineral admixtures as much as possible. Then we can keep the steel inside concrete in good, stable condition. David-san, is it okay? Surya-san. So in our laboratory now, testing the effectiveness of cathodic protection for CO2 mixed concrete from initial condition, initial age.
Oh, sorry, Hamada Sensei, can you hear my voice?
Yes, yes. Thank you.
I'm sorry for this trouble. Thank you very much for answers to question. And the next question from Miss Aya. Miss Aya. Miss Aya. Already. Okay. Thank you. Sorry, for the next question is from Mr. Dian. What do you think about the utilization of seawater on the viscoelastic material such as asphalt?
Sorry, we don't have experience to use it. Sorry, we don't have a data. But I think we should try. We should try.
Okay, thank you so much for your answer. Maybe for the next research project, Mr. Dian can initiate this kind of project, seawater mixing in or seawater evac in asphalt structure.
Yes, yes. Oh, so, yeah, this is the answer. Yeah. Hi, thank you very much. Collaboration.
Well, Dion, I think you cannot use seawater for the asphalt.
No. Sorry.
Yeah, the asphalt is, should be without water.
So it means resin concrete, Dian-san, or aluminum cement or something like that.
If no more question, maybe thank you very much, Hamada Sensei, for your very kind presentation and answer some question. And if there is other question, then we will summarize and we will send you by email the question.
Thank you.
So thank you so much.
Thank you very much.
Okay, ladies and gentlemen, thank you very much, and we are very sorry for so many technical problems during today's conference. Yeah, but we have to move on to the third keynote speakers, Professor Wei-Sing Huang from National Central University of Taiwan. So good morning, Professor Huang. Yeah, let me show you the brief CV of Professor Huang. This is Professor Huang's CV. So Professor Huang is a professor in the Department of Civil Engineering, National Central University, NCU, Taiwan. So his research interests are cement and concrete material, utilization of industrial waste as construction material, and barrier material for disposal of radioactive waste. So yesterday, Professor Huang already sent to us a recorded video. Is it okay if we play your video now?
Yes,
Professor
please do that. To be honest,
okay,
I'm the first-time user of Zoom, so it would be much better if we play the video.
Okay, thank you so much for your permission. So please, technical committee, please proceed Professor Huang presentation. We hope there is no more technical problem of playing video again.
Honorable guests, ladies and gentlemen, good morning. My name is Wei-Sing Huang. I am from National Central University in Taiwan. In the past about 6 to 7 months, the COVID-19 pandemic has created a barrier among people all around the world, making it not possible for researchers like us to get together and exchange new ideas. Honorable guests, ladies and gentlemen, and good morning. My name is Wei-Sing Huang. I am from National Central University in Taiwan. In the past about 6 to 7 months, the COVID-19 pandemic has created a barrier among people all around the world, making it not possible for researchers like us to get together and exchange new ideas. Honorable guests, ladies and gentlemen, and good morning. My name is Wei Shen Huang. I am from National Central University in Taiwan, Yogyakarta. In the past about 6 to 7 months, together and exchange new ideas. Honorable guests, ladies and gentlemen, and good morning. My name is Wei Shen Huang. I am from National Central University in Taiwan, Yogyakarta. In the past about 6 to 7 months, together and exchange new ideas. Honorable guests, ladies and gentlemen, and good morning. My name is Wei Shen Huang. I am from National Central University in Taiwan, Yogyakarta. In the past about 6 to 7 months,
No.
together and exchange new ideas. Honorable guests, ladies and gentlemen, and good morning. My name is Wei Shen Huang. I am from National Central University in Taiwan, Yogyakarta. In the past about 6 to 7 months,
This is not working. Well, no.
together and exchange new ideas. Honorable guests, ladies and gentlemen, and good morning. My name is Wei Shen Huang. I am from
Okay. As I mentioned, I'm the first-time user of Zoom. Let me see if I can share my documents. Give me a second.
Dr. Huang, at the bottom of screen,
Yes.
you can see share screen button.
Yes.
Yeah, and you can just click.
Yes.
And then you may designate the screen you want to share. Then.
Okay. Oh. Well. I don't know why I don't.
Okay. Is it possible, Professor Huang, to share your screen?
Well, yeah, I'm trying, but let's see.
Okay.
No, I need
the problem still occur.
Yeah, I got a message that I am banned from sharing.
From technical committees, could you allow Professor Huang to?
Now,
it's already.
yeah, Professor Huang, you are now co-host, so you should be able to share screen now. Please try again.
Are we okay now?
Yeah.
Yes.
Right.
Okay.
Oh, okay.
You got it.
It's very good.
Oh,
So
okay.
yeah, we are very sorry. And
well,
if you,
as I mentioned, I'm the first-time user. You can tell from the reverse background I'm using. I cannot do anything about it. Okay, since I'm more a Google person. Well, okay, let's get started. Yeah, it's been a nice experience for this virtual conference. I take it a completely new experience for me. So I like to thank the University of Hamada, Yogyakarta, for organizing this virtual conference. And I feel great honor to present a keynote speech to the symposium. Okay, my topic today is coupling of the thermal hydromechanical processes of buffer material in a deep geological repository. Oh, it doesn't move. Oh, I can't get it going.
Professor Huang, can you move to the next slide?
Yeah, okay.
Okay. Please.
All right, it works now. Okay. This schematic is the deep geological disposal concept adopted by Sweden and Finland. Both are pioneering in the task for the final disposal of radioactive waste. As can be seen here, that the spent nuclear fuels are to be deposited to the disposal tunnels about 500 meters underground. So one of the major engineering barrier surrounding the canister is called buffer material and is made of bentonite clay. So the evaluation of the coupled heat transfer, groundwater movement, and stress changes in the buffer and the deposition hole is an important issue in the safety assessment of the underground repository. This slide shows the timeline for Taiwan's final disposal project. Yes, the 5-stage project is going to take 50 years or half a century. Well, this is typical for many countries, as Sweden and Finland both started their task as early as 1980s, and almost 40 years has passed. The latest development is that Finland just started construction about 1 year ago, while Sweden is still waiting for the final approval from the government for the construction license. So this is really some kind of a lifetime project. Take myself as example. I spent the past 15 years on this and have graduated more than 30 master and PhD students on the subject. But it's not likely that I'm going to live long enough to see the opening of the repository. Okay. So in this study, the buffer material or bentonite clay used as the engineered barrier is characterized in view of an unsaturated soil. In other words, material characteristics such as soil suction, hydraulic conductivity, and thermal conductivity of the clay material as a function of the degree of saturation are incorporated in the experimental program and numerical simulation. As an important component of the engineered barriers, major functions of the buffer material are to reduce the groundwater flow, to protect the canister from instability and degradation, and to retard the migration of nuclear recline. So estimation of the heat transfer, groundwater movement, and stress changes in the clay barrier, and evaluation on the impact of these changes on the sealing function of the clay barrier is an important issue in the safety assessment for the repository. So with considerable development in the area of unsaturated soils over the past two decades, it is felt that the material model of this unsaturated buffer material can further be attacked to improve our understanding on the saturation process of the clay barrier, with emphasis on soil suction, hydraulic conductivity, and thermal conductivity of unsaturated clay barrier. The clay barrier used in this study is a commercial clay available domestically in Taiwan called Rixing clay. It is characterized as a calcium type bentonite with a high content of impurity. In addition, Black Hill bentonite out of Wyoming, USA was also used as a reference material in the study. And Black Hill bentonite is a sodium type bentonite with extremely high plasticity index of 380. This figure shows the pore air water configurations of unsaturated soils at various degree of saturation. In a state of very low degree of saturation, water is occluded by air and soil grams, and the suction or pore pressure can be extremely high. As the degree of saturation increases, air becomes occluded and the soil suction drops significantly and approaches zero at about 100% saturation. The relationship between relative humidity and soil suction is given by Kelvin's law. Here, UA and UC are the air and pore pressure, respectively. P is the partial pressure of the pore water vapor. P over sub-zero gives the relative humidity. Therefore, it is possible to control the suction in the soil mass by imposing the relative humidity of the environment. The vapor equilibrium technique was carried out by using several selected salts for control of relative humidity in the incubator, maintained at constant temperature. For example, the first line here, potassium sulfate will provide a relative humidity of 97.2 at 25 degrees centigrade. So clay materials were compacted to the design density and placed in the incubator along with the saturated salt solution. Typically, it took about 6 to 10 weeks for the vapor to reach equilibrium with the vapor pressure or suction in the soil mass. What is unique in this study is the soils, the soil suction were determined for not only room temperature, but also at elevated temperatures of 40 and 60 degrees Celsius. Then we were able to determine the relationship between soil suction and degree of saturation. And this is called the soil water characteristic curve, or SWCC. For bentonite specimens at high degree of saturation, the thermocouple psychrometer was used for measurement of soil suction. This psychrometer is frequently used by researchers in agronomy. Okay. So then a complete soil water characteristic curve can be obtained with the combination of water equilibrium technique plus the use of psychrometer. Then we were able to determine the relationship between the soil suction and degree of saturation. So the general empirical equation proposed by Friedland and Singh were used to fit laboratory data over the entire suction range. S is the degree of saturation, C is a correction factor. So this is basically a graphical estimation of the three parameters derived from a semi-log plot of the soil water characteristic curve. First, we will find the L entry suction value and then the parameter N and N. Basically, this is a nonlinear minimization curve fitting process. The resulting soil water characteristic curve for black hill bentonite at elevated temperatures are shown. In general, soil suctions decrease with the increase in temperature. And the suctions of black hill bentonite are found to be higher than those of Zhixing clay due to its high plasticity. Then, in addition to soil suction, the hydraulic conductivity is another important variable for unsaturated soil. First, the hydraulic conductivity of clay material in a saturated state was determined for the two bentonites using traditional rigid wall permeability test. Again, at various elevated temperatures. And then the relative hydraulic conductivity of unsaturated soil to the saturated soil can be predicted from the soil water characteristic curve. The relative hydraulic conductivity is an integration form of the soil suction versus water content relationship. The calculation was performed by dividing the relationship between volumetric water content and suction into m equal water content increments. With the soil water characteristic curve shown, the relative hydraulic conductivity of the two bentonites can be derived, as shown here. It is observed that the hydraulic conductivity of a single soil ranges over about 8 to 9 orders of magnitude when considering the soil from a dry state to a saturated condition. Then the thermal conductivity of the two bentonites was determined by the thermal probe method in accordance with an ASTM test standard. The results are shown here. Okay, then a series of water uptake tests was performed at various temperatures for several weeks to observe the saturation process. After the test, the specimen was extruded from the mold in about 5 millimeter slices and determined for their water content, such that a degree of saturation profile along the distance from the water inlet can be obtained. Now, numerical simulation of the water uptake test, incorporating those material characteristics of unsaturated clay material, was carried out at various temperatures. Okay, these are the initial and boundary conditions and the material properties adopted in the simulation. The final element calculation was performed using Abacus program. These curves shows that the experimental results and numerical simulation exhibit good agreement in terms of the degree of saturation profile. Okay. So this figure shows the detailed degree of saturation profile and void ratio profile here. It is noted that the lower part of the specimen swells upon the uptake of water, while the upper part becomes dense under the swelling pressure from the lower portion. Finally, the material model used with success in the water uptake test simulation was extended to the simulation of the deposition hole. This figure shows the final element mesh adopted in the actual symmetrical analysis. This slide shows the initial and boundary conditions and material model used in the numerical calculation. The heat flux generated by the canister is shown as a function of time. Then this slide shows the initial and boundary conditions and material properties used in the simulation of saturation process of the deposition hole. Okay, this figure shows the results of the heat transfer simulation with temperature distribution. And at the right-hand side, we have the results of the saturation process simulation. And here it shows the degree of saturation distribution in the near field of a deposition hole. Finally, I like to show two videos of our recent development. With success with the simulation on deposition hole, we were able to extend that procedure to the simulation of two parallel disposal tunnel, each with 9 deposition hole. So this is a simulation for 100 years of heat transfer, the thermal evolution of the disposal tunnel. Yeah, it's still running. From the emplacement to 100 years for two parallel disposal tunnel. Okay, this is for the thermal evolution only. The next slide will show the coupling of thermal, hydro, and mechanical effects. No, the next one. Yes, this one shows the coupling of those three effects together, again, for the two disposal tunnel. This video shows the saturation process for 20 years. Okay. Here comes the conclusion. Well, I'm not going to read it. Basically, since the emplacement of the spent nuclear fuel. The buffer material is in an unsaturated condition. So the suction of the bentonite clay are really of great importance, especially at the early stage of the repository. And the simulation of the saturation process of the clay barrier, the coupling effects of thermal hydromechanical process show significant impact on the state of the clay barrier. So after this THM process, the repository will serve for at least 100,000 years. Okay, so that's actually the initial state for the long-term safety analysis. Okay, so that concludes my presentation. Thank you for your attention.
Thank you so much, Professor Huang, for your very nice presentation. Yeah, we are very sorry for the technical problem. We cannot play your recorded video. Okay, let me invite questions from the audience. So first question from Professor Agus. So the question is, do you model the leakage effect of the water materials in your research?
Yes, that's a good question. In the vapor equilibrium method we adopted, the shrinkage part is not creating much problem. We use a detailed photogrammetric method to such that we are able to determine the final volume after the drying process. But we do have more difficulty. We did experience more difficulty on this saturation on the saturation stage, because we experienced an incredible amount of expansion, swelling, okay, upon saturation. So yeah, that's about it. We actually used the soil suction. I think we determined the correct soil suction in the dry side of the process.
Okay, thank you very much for your answer. And the second question from Professor Agus, what is model used for shrinking?
I didn't get that, excuse me.
Maybe you have a simulation or model for shrinking in this research? Okay, yeah, sorry. And we move to the question from Professor Kim. Which finite element package did you use for the THM couple simulation? And what was your computational cost for the simulation?
Oh, okay. That's a good question. That's a really good question. Yes, actually we use very fine finite ash for the simulation of the water uptake test, and up to the simulation on the deposition hole. It takes somewhere like 1 to 2 days using a notebook, using a desktop computer for the simulation of the deposition hole. For the calculation on the two parallel disposal tunnel. A lot of simplification was adopted. That's a lot to talk about. Okay, it takes so much in this simplification process. Okay, I think it will take forever if you use a fine element mesh for the calculation.
Okay, thank you very much for your answer for Professor Kim's question, and I think it's time. Thank you very much, Professor Huang, for your time and for your very nice presentation. Once again, we are very sorry for the technical problem. Okay. And now we will move to the last keynote speakers. Professor Agus Setio Muntohar from Department of Civil Engineering, Universitas Muhammadiyah, Yogyakarta. Professor Agus is also adjunct professor in UNESCO Chair, Geo-Environmental Disaster Reduction. His research interests are landslide and slope stability, soil improvement, numerical method in geotechnical engineering, sustainable materials, and liquefaction analysis. So today, Professor Agus will deliver a keynote presentation with the title, The Potential Uses of SICC for Improvement of Geotechnical Structure on Expansive Soil. So Professor Agus, please proceed to your presentation. Can you hear me, Professor Agus?
Yes. I need to check this. This already displayed.
Okay, yes.
Is it full screen,
yes.
Mbak Bintan?
Yes. I think everything okay on your share screen.
Okay, this is already in the full screen or not? I need to check it.
This one is a speaker view.
Okay. Yes, thank you.
Okay, now, okay.
Okay, thank you. Good morning and good evening, Professor Kim and all the audience and participants. Honorable keynote speakers, Professor Kim, Professor Wang, and Professor Hamada. Today, I would like to present a part of our studies in my basic group. So the title for our presentation today is the potential use of the SICC for improving geotechnical structure in expansive soils. This research has been sponsored by the Ministry of National Education, start from 2012 to 2015, and continued with the Ministry of Research, Technology and Higher Education in 2016-2017. Basically, this research is we try to use waste materials as the stabilizer for soil improvement. And then for today's presentation, because we have many slides, but I will go faster. This is our content presentation. I would like to present the introduction, background, and also develop the research, how to categorize and do reliable tests, and also small scale tests and numerical modeling and clinical image. Okay, let me start the first analysis. In Indonesia, we have many roads have been construction over the expansive soils, especially in Java Islands. And also we start from the 3 years ago, we also construct the toll roads along the Java Island in the north. Some of the toll roads was constructed on the osmotic soil. And then in Yogyakarta, we also have some location of the route highway was construction on osmotic soils. Okay, this is the typical of the highway damage, due to the swelling and shrinking of the osmotic soil in area in Yogyakarta and also in some in the other area in Central Java. Okay, due to the damage of the road pavement were observed due to the loss of strength during the swell and shrink cycles. So this is the typical of the road pavement damage in Jakarta, and also this one. And then the Ministry of Public Work to repair the pavement damage. This is just simply they are doing for the overlay because the overlay is was the quick method, but unfortunately this method was ineffective to overcome the expansion of problem for subgrade. This is the issue. Then during this our research, we try to overcome this problem. And then for this one, for today, this research proposed to the new technique to improve the strength of the subgrade of pavement system by introducing the SICC column as the foundation of the flexible pavement. What is the ICC column? ICC is the one of our research patent to Ministry of Indonesian Patent Office. Okay, this is our method, proposed method, how to do some improvement in the survey base layer. This is if we need to improve the base layer, we just install this ICC column to the subgrades, and also we can also introduce the column start from the asphalt, and then this is for the type 2. Type 1 is if we will do the soil improvement before during the construction. But if the construction the damage, we can also install the column. Start from the surface layer to the subgrades. This is the type 2, and also the type 3. We enlarge the column cap to have the better bearing capacity and also the bearing of the subgrade and also subgrade and base layer. Okay, this is our proposed method. Okay, let me start. I skip this one. Okay, this is the ICC what we are what we are used in our research. This is this ICC has been researched for the patent. This is the number, and then I'm the one. I'm the inventor. This is the characteristic of the SICC. Okay, this is based on the ICM. It's mainly this ICC is one of the cemented materials. And this is we compare with ICC and the cement. And then in total, this is the characteristics. Okay, the setting time and also the thermal consistency. Okay, this is the setting time is I think almost similar with the Portland cement, and also the normal consistency if the ratio. Okay, the ICC basically the mixer between the calcium and also silica from the waste materials. Okay, this is the characteristics. Yeah. Okay, this is for the SICC, the strength of the ICC, the test. And then based on this result, we have that this is the optimum composition of the ICC. In 2013, we applied our SICC, to be used for pedestal for lightweight structure. We construct this lightweight structure like the gazebo from our university, inside our university. This is as the pedestal lightweight structure, and now this construction is exists in the right now. And then the other method is this one to use for the soil improvement of toll roads. Okay. This is the what we are doing in the toll roads. Our cemented material. Okay. And then for the next things, this is this is the method how to use for the surface for the subbed improvement using the ISO method. This project is construction 2 years ago in one of the project in West Java and Banten. Okay, this is for if we want to know the the stiffness. We did also some model in laboratory to determine the strength, the stiffness characteristic of the ICC column. This is our model. We did some unconfirmed strength tests, and then this is the result. And this is the model's information. This model's information is needed to as the input parameter for the numerical analysis. And then we did also some small physical model CC for the supported flexible pavement. Okay, in laboratory. This is the results. We model this is as the flexible pavement, and this is our column. This is the model in the small scale, and this is for the numerical modeling. If we see here that there is some benefit if we install the column SSC column in the to support the flexible pavement. Okay. This means that there is the increase for the bearing capacity of the flexible pavement. And then this is also the small physical model for ICC column support flexible plates. Okay, we did also so we increased the model from the first model to the single column model. This is what we are doing in our laboratory. Okay, and then this is the results. This is of the no column support, and this is if there is the supporting column. Okay, we did some different column size and length. Okay, and this is for the T-shape. This means that there is if we install also the larger column, okay, this is better than the shorter column. And also this is one, if we use the O-shape column, if we enlarge this column cap, this means that the settlement in the formation, the deflection of the flexible plate is lower than the O-shape column. This is our calculation, and then also this is from the laboratory tests, and then we did some also verification with the numerical modeling. Okay, this is our model. This means there is the laboratory and this element analysis. This is and then we tried from this our laboratory model, and then we try to do also some the other model in our laboratory. And this is we also do some laboratory, and this is the result from our load and deformation analysis. The maximum load for our model is about 30 kilonewton, around about 3 tons. Okay. This is the typical of the T-shaped column after the test. Okay, and this is what we extend our laboratory test to our numerical model. Okay. This is our monocle model. And then we try to, before we apply to the field, okay, we try to model our laboratory test to be applied in the field. Okay, we did some numerical modeling. Okay, this is the deformation during the swelling and loading. If the flexible pavement is unsupported with the column, that is the difference settlement is larger. But after we install the column based on our numerical modeling, this is the column can reduce the difference settlement. And also, if we try to install the column start from the surface, and this is they can also reduce the difference settlement of the pavement. But still, the swelling is still the swelling is not uniform here. But if we use this method, the type 3, we enlarge the pile cap. You can see based on our model, the swelling is almost uniform in the cell surface, and also the T-shape definitely reduce the difference settlement. For example, this difference settlement about 1.2 millimeter, and this is if we compare. This is 4 millimeter for the type 2, and this is for the type 1 is about. Okay, this is the type 1 is about 4.4 millimeter, the maximum difference settlement, and for unsupported about almost 5 centimeters difference settlement. Okay, this is the based on this and we let me to what's it called to end our presentation with the concluding remark. The ICC column system as a foundation system of pavement has shown a superior to reduce the heaving and difference settlement and improve the strength of the pavement effectively. And then full-scale model test is made to investigate and the performance and reliability of the combination for cycle. Because our test still in the laboratory, okay, we need to also apply the other research grant for this year to be applied at the full-scale test model. I think this is still in this there is a problem. If we install the column in the field, there is some protrusion problem, okay, near the column. This is where we install. So we need to also to think about this problem. That's why the solution to enlarge the pile cap, this enlargement of the column cap maybe can reduce this protrusion problem in the support the flexible pavement. This is our remark. And then thank you for your attention. Okay, hopefully this presentation will have the fruitful discussion for the next session. Thank you.
Thank you very much, Professor Agus, for your very nice presentation. And let's move to the Q&A session for Professor Agus. Is there any question from the floors? Yeah, from a question from Professor Kim. Thanks for your presentation. What would be cost for the method compared to conventional way like lamp cement stabilization?
Thank you, Professor Kim. This is for your question. The compare if we use this product, because this product is low. This is low middle technology. So this products no need to high technology. So when we use this product, the ICC, compare with the cement, not like cement, but cement stabilization, we compare, they can save the cost almost 40%. Almost 40%. This means that based on the cost, the product is cheaper than cement stabilization because we can also reduce the overhead of the production. if we use the cement, because cement is I think they need some high technology, because in Indonesia what we need in Indonesia is low to medium technology the product. So this product can be produced by local local and the small enterprise in our society. This is the issue. So this is the issue. Yeah. Thank you, Professor Kim, for question.
Okay, thank you so much, Professor Agus, for your answer. Is there any other? A question from Dr. Puji Harsanto for Professor Agus. Can we use the product for underwater conditions?
Thank you. We're not sure because this we haven't tried this SSCC as the for underwater condition because we never tried. So I have no data to answer the question.
Okay, thank you. Maybe still other participants want to give question for Professor Agus, or maybe from another keynote speaker, maybe. It's very welcome. Okay, if no more question. Thank you very much, Professor Agus, for your time, for your nice presentation. So yeah, thank you very much for all keynote speakers. Many new information we have got today. So those all are very interesting and inspiring knowledge. And as we heard from the speakers, many improvement of the construction material. So there are still many limitations. And now maybe I would like to ask each speaker or all of you about your comment or your expectation for future improvement of material engineering science. Or do you have any idea about this topic? Maybe first from Professor Kim. Professor Kim? Okay. You are in unmute now.
Okay. Can you hear me now?
Yes.
Okay.
Please.
Yeah, somehow I was not allowed to speak. Well, I think, again, thanks again for invitation and great event. I enjoyed a lot. And I think this is excellent event and great to be with you, Indonesian community and other excellent scholars from Japan and Taiwan and other countries, and great. Well, regarding to that question, I think my concluding message, like for the materials, I think we really want to collaborate with the scientists, material science people, chemistry, physics, so that we can do better engineering. I think a scientific investigation really help for our better development and technology for the future. So that's what I'm trying to do. I'm sure many other professors and researchers do the same job. And if you think about like a National Science Foundation funding opportunity in the United States, without collaboration, without multidisciplinary aspect, it's really hard to get funded. So I think that that's a direction, and I would say that is the way we should be doing for the future.
Okay, thank you very much, Professor Kim. Next move to maybe Professor Hamada. Maybe do you have any idea or any suggestion for this kind of topic?
Thank you. So I think the trend of concrete engineering is, one trend is for low quality material usage. So I think it is, how can I say it, somehow easy to construct with high quality materials. However, now it is difficult to use enough high quality material all over the world for profiles also. So I think from now, low quality with low quality material and construct high quality construction. And also one more keyword is local. Local material is requested to use effectively. So every area there is a concrete engineer and also concrete researcher. So it is requested strongly to use local, rather low quality material for construction in 21st century, I think. This is a one. Thank you. Thank you, Pinto-san.
Thank you so much, Hamada Sensei, for the highlight of local and low strength material. And next, we move to the third keynote speaker, Professor Huang. Do you have any idea about this matter? Professor Huang? Okay. Sorry. And we move to the last keynote speaker, Professor Agus. Maybe do you have any idea or your plan about this kind of topic?
Yeah, thank you. Let's see. The first, we are very thanks to the Professor Kim, Professor Hamada, because I think this is the initial point from this for this symposium or for this conference to build a very strong collaboration between the developing country and developed country. So I think from Japan and also US also we can also share our experience, and then also we can also adopt its technology. But because Indonesia, because we need to also to build up and also to strengthen our local enterprise. This means that the technology we still have the high technology, but how the high technology can be transferred to local enterprise, this is the point. So it means that we can also think about the high tech, but how the application can be used also for the local people, for our local society. This is the point for in our country. Hopefully, for the yesterday, I got some got from the news from our industrial partner from one of our government enterprise for the construction. They will use our product for the toll road for the other section in Sumatra. So it means that if possible, maybe we can also collaborate to, especially to develop the testing method for the field, because the issue in the ground improvement using our method is the uniformity. So how to measure the uniformity of the quality of the strength during the whole the roads. This is the issue. This means that for the next, I think we can also collaborate for the testing in the field and to determine the strength of the field directly, and also to use like the quality control and quality assurance of our methods in the field. I think this is our comment. And again, thank you for the Professor Kim and also for Hamada. I think this is the very important point to collaborate between us, between our university and also the Texas and also QC University. And I think this is the final, the end of our comment. Thank you. Thank you. Thank you.
Thank you so much.
Okay, thank you so much, Professor Agus, Professor Kim, Professor Hamada. So I will remind to all participants before closing, the Secretariat already provide the questionnaire about your feedback during join this conference. So please fulfill the questionnaire. Okay, so As the closing statement from me, on behalf of organizing committee of CIMAPS 2020, we would like to thank you for all contribution of keynote speakers and participants during today's conference. Yeah, we are very sorry for all technical problem, and we hope to see you directly after the COVID-19 pandemics and extend the collaborative program between our university and your institution. Please come to Indonesia, to Yogyakarta for Professor Kim, Professor Hamada. Maybe Professor Hamada hope to visit Yogyakarta again after 15 years ago. We are really hope to see you again.
Maybe next year.
In Yogyakarta.
Maybe next year. Next year.
Maybe next year. We really hope to meet you directly in Indonesia.
We still have another conference next year.
Okay. Okay. Thank you, Professor Agus, for your information. Okay, maybe for me, thank you very much, and see you again in the next event. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much, Professor Hamada, Professor Kim, Professor Agus, and all participants.
Thank you so much again.
Thank you so much, Professor Kim. And then
keep in touch. All right.
Yes, keep in touch by email.
Sure.
Thank you. Bye. Good
night.
Going to go to bed already.
Yeah, it's time to think about it.
Thank you.
Great to see you guys then. Hey.
Great to see you.
Bye.
Mana Mas Dian? Mas Dian langsung dijelasin dengan profesornya.
Yeah, it's time to think about it. All right. Great to see you guys then. Hey.
Good to see you.
Bye.
Mana Mas Dian? Mas Dian langsung dijelasin dengan profesornya.
Paradigma pendidikan kami adalah
it's time to think about it. Great to see you guys then. Hey.
Ilmu dan teknologi secara kreatif, inovatif, dinamis, dan berkelanjutan.
Mana Mas Dian? Mas Dian langsung dijelasin dengan profesornya.
Paradigma pendidikan kami adalah
it's time to think about it. Great to see you guys then. Hey.
Ilmu dan teknologi secara kreatif, inovatif, dinamis, dan berkelanjutan.